Hi guys, so for 3.6 we are going to be talking about transformations of functions that we already know solutions to and then figure out what those transformations tell us about our new solutions for a transformed graph. So let's just jump right in so you have actual examples here. So this starts making sense. So I'm going to use a couple of equations that we did in Math 3. So I'm going to use the equation, the graphing form of an equation that we used for parabolas. So that was a times x minus h squared plus k. So we spent a lot of time on this at the beginning of Math 3 and discussing what the parameters a, h, and k did to the parent graph of y equals x squared. We also looked a little bit at the equation of a circle. So that was x minus h squared plus y minus k squared equals r squared. And we looked at what h, k, and r did to the parent graph of this, which was x squared plus y squared equals r squared. So hopefully you are remembering that. Well, let me go back here. This transformed the graph of y equals x squared. There we go. So the parent function x squared, which usually has its vertex at 0, 0, when transformed by h and k, which we found in the graphing form of an equation, it moved the vertex. And a, we saw, would either vertically stretch or compress it. And then we saw this a similar pattern here with h and k. For the center of a circle, which would have started at 0, 0, h and k would transform that. H transforms things left and right, and k transforms things up and down. So we're going to take our previous knowledge on transformations and add on to that in this section. So when we replace x in an equation with x minus h, just like we saw with parabolas and circles, and when we replace y with y minus k. So this makes sense with the circle, but with the parabola, this k is over here. Well, all we would have to do is subtract k from both sides, and then k would be with y. So when we do that, we see all of the x values shift to the right h units. This is assuming h is positive. So it would shift to the right k units. Whoops, no, h units. And it would shift up k units. So again, that's assuming h and k are positive. If h was negative, it would shift to the left. So replacing x with x minus h and y with y minus k. So we have a new notation that I'm going to introduce you to. It's called transformation notation. And it's a capital T and then a little xy, often in the subscript. I just can't write that small on this tablet. And then the transformation rule itself is what the transformation notation should give you. So it is x plus h, comma, y plus k. So let me give you a quick example, because sometimes this is the confusing part. So if I had the equation for a parabola, y equals, let's just do x minus 2 squared. So let's just say that was my parabola. Then this tells me that h is positive 2, right? Because it's x minus 2. So h itself is 2. This means I would shift the graph, every point on this graph, 2 units to the right. Transformation notation, so this is the equation, but transformation notation tells us exactly what to do to x and y. So it says the transformation would be take all your x values and add 2. Take all your y values and just leave them the same. So this is not an equation. It's basically telling you the rule. What is the rule to do with all my x's? So it's transformation notation tells us the rule, whereas in the equation, it just gives you the value of h. So in the equation, it's x minus 2. The rule itself is add 2, because we're adding h to all of our x's. So big difference between the equation itself and then the transformation rule. So now we're going to look at scale changes. So scale changes we saw appear right here in A in our equation for a parabola. So when we replace x with x over A and y with y over B, this is going to seem weird because we didn't look at it like this last year, but just hang with me. When we replace x with x over A or y with y over B, then we change the horizontal magnitude of the graph by multiplying all of the x's by A multiplying x's by A, and then we change the vertical magnitude of the graph because y's would be multiplied by B by multiplying y's by B, multiplying y's by B. So before I get to transformation notation, let me break this down with the equation of a parabola because you're probably angry right now at the fact that it's opposite. So right now, if I had a parabola and I had 3x squared, let's just leave it like that. So in this case right here, we would call this the A value, typically, right here. This is my value of A, and that's what this would produce a vertical stretch of 3. So any x value that I plugged in and squared, I would actually take that, what would be my original y value, and triple it, and that's my new y value. So even though this is over here with the x's, it is actually affecting the y values. So we called this graphing form, but what's really happening is if I put that 3, with the y, what I would do is divide both sides by 3. So I want anything that's affecting the y values with the y value. So then this would give me a new equation, y over 3 equals x squared. So it's just another way of writing equations. I want anything that's affecting the y's with the y's and anything affecting the x's with the x's. So where I saw this 3 on this side of the equation last year in form of A, it's actually affecting the y's. So we're just writing it a little bit differently so that we are keeping those things that are changing the y's with the y. So what these do are, change it vertically with vertical and horizontal stretches. The transformation notation, again, it's the actual rule. So I don't have enough space on that line, so I'm going to write right below it. So the transformation, maybe I do have enough space. The transformation on x and y. So this is what this new notation means. The transformation on x and y takes those normal x and y values and it takes them to, so what this is saying, all of the x's being multiplied by A, so it would be, again, it's the actual rule. Multiply x by A, multiply y's by B. So again, it appears as the actual opposite of what you see in the equation. So just like up here we had x minus 2, the rule itself was add 2 to all the x's. So in here I see y divided by 3, but the actual rule itself, transformation rule, that would be t, the transformation on x and y, takes x and y to 3 regular x's, 3y. So this regular, nothing happened here with the x. There's no variable, or there's no value inside the x squared that's affecting x. This 3 is actually tripling the y's. So this would be the transformation rule. And again, it appears as division in the equation, but the actual rule itself is multiplication. Okay, so let's look at another example and relate these transformations to a graph. So in example 1, we're going to graph the function f of x equals x cubed. You should be able to graph this function on your own. This is the parent function for cubics, and you can plot some points here. So when I plot, plug 0 in and cube it, I get 0. When I plug 1 in and cube it, I get 1. go over 2 and cube 2. The output is 8. So 2, 4, 6, 8. And then I'll go into the negatives as well. Cube -1, and your output is -1. Cube -2, -8. So a quick sketch of f of x equals x cubed. And again, this should be review. Now it says on the same grid in a different color, graph x minus 2 cubed. Based on what we are hopefully now remembering about transformations, this is my parent function, x cubed. X minus 2 cubed. This is my h. I'm actually just going to shift everything over 2 units to the right. So h is positive 2. So I'm shifting everything. So on the same grid in a different color. So all I have to do is take every single point and shift it over 2 units. So this is what's happening visually to the graph when I perform this transformation. Okay. So next we're being asked, how are the zeros of f and g related? So f of x was our original, this is f in pink, and then g of x is the transformed. How are the zeros related? Meaning, how does the solution to this versus the solution to this change? When does this solution equal 0 versus when does this solution equal 0? Well, visually we can see right here x cubed equals 0 when x equals 0. And algebraically we can see that by just taking the cube root. The 0 would be 0. Thinking about this one, when does this one equal 0? Well, visually we see that crosses the x-axis. Y equals 0 right here when x equals 2. Algebraically, I could take the cube root of both sides. Cube root of 0 is 0. Add 2 and I would get 2. But the whole point of understanding transformations is that if I know the solution to this one and I know the transformation, meaning shift everything right too, then I should be able to go from this solution right here directly to this solution without actually needing to solve this. Because if I know this solution is being transformed in this way with adding 2 to all the x's, then I can arrive at this without really solving the transformed equation. So back to answer this question, how are the zeros of f and g related or mapped? They're just shifted right 2 units. And then we could think of this in terms of chunking as well. When we look at this equation, x minus 2 cubed, we could chunk that, I guess, and again, which just means substitute, and let t equals x minus 2, and then you would just have t cubed. So you would find the solution for when t cubed equals 0, and then plug x minus 2 back in right here. So let's think about this in terms of transformation, and this is what I want you guys to be understanding here, is that this function is a transformation. So I'm going to use transformation notation. The transformation on x, y, it takes, what this means again is it's transforming x and y. It takes all the regular x's and y's from this parent graph, and the actual rule, what it's actually doing is adding 2 to all the x's. I'm not changing the y values. So again, the only change in the equation is x minus 2 cubed instead of x cubed. So in the equation, it's x minus 2. The transformation rule is x plus 2, what you're actually doing to the x values based on this h value. So again, we can now transform any point from this parent graph to this graph using the transformation rule. So let me show you an example of using a transformation rule. So if I want to transform the point 0, 0, which would be right here on my parent graph, I apply the rule. Take 0, 0, add 2 to the x coordinate, which is 0 plus 2, and keep the y coordinate the same, which is 0. So that would be 2, 0. So I know that's blatantly obvious by looking at this visual, but I'm trying to help you guys understand this new transformation rule writing and how that applies to any coordinate on a function. So it's basically just saying what would I do to every single point on my original function, and then you can transform any specific points on that. So let's take another quick look at a different example on the next page. Okay, so looking at this one, I just want to graph and solve this inequality, and then we'll look at the transformation. So this inequality right here, we want to know when that quadratic is less than 0. So let's think about what that quadratic looks like. So we've got x squared minus 5x plus 4. And we want to know when it's less than 0. So if this were an equal sign, we want to know where this equals 0, we would just factor and solve. It's not the same process for inequality. So I'm going to show you a new method called the test point method, and that is a method you're going to need to be able to use. It comes in handy when we're finding solutions to inequalities. And it's called the test point method because you test points during this method. So the test point method in finding out, again, when this quadratic is less than 0. The first step, which you'll like, is just replace it with an equal sign first. We're going to find the boundary points. And I'm going to factor this. And like I said, if this equaled 0, we would just factor this and solve. So let's factor. And I want something that multiplies to 4, adds to negative 5. That's going to be x minus 1 and x minus 4. So x minus 1, x minus 4. Okay, so this gives me my two solutions of 1 and 4. That's where the function equals 0. So again, these are just my boundary points, not the solution to when this inequality was true. So this is when the equation is true. So these are my boundary points, and that also means these are my x-intercepts at 1 and 4. So if I was going to start graphing this, that's where my x-intercepts would be. Now, to figure out whether or not this quadratic is positive or negative around these boundary points, in the test point method, once you find the boundary points, plot them on a number line, and then what we're testing, we plotted the points, now we're going to test. It's called the test point method. I want to figure out if this is where the equation equals 0, or where that parabola equals 0, then that means it must change from positive to negative before or after these points. So we want to figure out on this interval, is it above 0 or below, above 0 or below, above 0 or below. So then you would just pick points and test them. So I would choose a point, any point less than 1. So for example, if I test 0, I'm plugging 0 right back into my original inequality, or I could plug it into the factored form, it doesn't matter. So if I plug 0 in for x, I would have negative 1 times negative 4, and that results in a positive number. So I'm going to put a plus sign right there that tells me that this quadratic is positive as long as x is less than 1. What about between 1 and 4? Again, I would pick a new value, so test a value between 1 and 4. So let's say I tested 2. So I would write testing 2. I would plug 2 in right here. 2 minus 1 is 1. 2 minus 4 is negative 2, which is negative. So my results are always going to be negative on the interval from 1 to 4. And then pick a number larger than 4. So again, it can be any number larger than 4. So let's pick 10. If I plugged it in for x, again, right here, 10 minus 1 is 9, so test 10, and that would be 9 times 6, which is positive. So here, this tells me that on this interval, the function is positive. On this interval, my function is negative, and on this interval, it's positive again. We were originally trying to solve when is this less than 0. So my solutions are this interval between 1 and negative 4. So that is my solution between these values, 1 to negative 4. So now let's see how this translates to the graph. So the graph of this parabola is, let me give you a couple points on it. So I gave you the x-intercepts, which are 1 and 4, and then there's 2 other points on the graph right here. But this graph generally looks like this, and then hopefully this all starts coming together here. Come on. Okay, well, I'm really bad at drawing parabolas on this tablet. Okay. So there's my parabola, and we can see visually that it's less than 0. The y value is less than 0 between 1 and 4. But algebraically, when is that less than 4? That's where the test point method comes in. So again, we find where it equals 0, and then we test points on the 3 intervals of the number line that those zeros break the number line into. So we see from that it is negative right there between 1 and 4. So now what we're going to do is on the same grid, graph in a different color, so I'll use pink here, this transformation of our original. So all we're doing with this transformation is changing all of the x's. So instead of x squared, it's x plus 3 squared. Instead of negative 5x, it's negative 5x plus 3. And then the plus 4 is the same. So I'm taking every single point on here and transforming them. The plus 3 indicates that I'm actually going to shift left 3. Because remember, if it's in the form of x minus h, the only way to have a positive 3 is if I'm subtracting a negative. So I'm going left 3. The chunking statement, if we want to think it in terms of chunking or substitution, would be let t equal x minus or x plus 3. And then the whole point of this is that now I have a solution to my original inequality, right? I have my original solution to my original inequality. So let me clarify. This tells us that the solution to this inequality has a solution of 1 to 4. That's the answer. That's the interval on which this parabola is less than 0, between 1 to 4. Now, graphing this new one, shifting left 3, 1, 2, 3, 1, 2, 3. So this would give me a new parabola, and because I know that the transformation rule itself is shift left 3, I can just take this solution and subtract 3. So apply the transformation rule to find the solution to this. The solutions to this, all I would do is take 1 and subtract 3. So my new solution for the interval would be negative 2, comma, and then take 4 and subtract 3, and I would get 1. So this is my new interval for the solutions for which this parabola, this transformed one, is less than 0. So instead of actually algebraically solving this more complicated looking one, I can find its solutions by solving the simpler one with the test point method, and then apply the transformation to my solution. So I apply the solution to my original one to that one. So the transformation rule, let me write the transformation rule since I've been talking about subtracting 3, but I actually haven't written it. The transformation rule took x's and y's and transformed them to x minus 3, comma, y. So that's why I took this x interval and transformed it to that x interval by subtracting 3. Okay, I'll stop here and clarify any confusion that may have occurred in this video in class as we move on to finish this section.